Okay, good day. So the first thing is that I'll be drawing the main diagram. And for the main diagram, I'm going to be reducing the ratio. So anywhere I see 10 centimeter on the diagram, I'm going to use 1 centimeter. That is, I'm using 1 centimeter to draw 10 centimeter of the original diagram. Yeah, looking at the diagram now, OA is so for OA we are using 3 centimeter, AB we are using 5 centimeter, and BB not we are using 3 centimeter. 3 centimeter. So let me draw the diagram. So I want to draw a diagram. So just draw a straight line here. Then the angle there, I think the angle there should be 70. So I'll first use my set square to draw the vertical and the horizontal line so that I can put my protractor on it to get a perfect 70 degree. So I'll use my protractor to look for 70 degrees. This 70 is 3 centimeters. So I'll draw 3, that is from 3. So if I check it, this 3. Yes, that's 3. Okay, so then AB now. AB, the angle to the horizontal, that is the angle here like this. AB, for AB it is 20. Just want to bring this same guy, bring it up here, and just draw a perpendicular line for it. Perpendicular line. A perpendicular line. I'll just measure 20 degrees. 20 degrees. So 20 degrees. This from 0 to 20. So this is my 20 degrees. And the length of AB is 50. So I'm drawing 5. So that is from here. So that is from here. Let me take it from 6 to 1. Here, this 5. So if I look at it, well, that's 5. Yeah, 5. And the last from the diagram, look at diagram. BB not, BB not is like 130 here. So this place is 130. This place 130. That means it's like this. BB not from the diagram. BB not something like this is 130 here, right? And this place is 130. That means this place should be 50. I'm going to straight line 50, right? It should be 50. So if I use alternate angle, here too should also be 50, right? So I'm going to draw a straight line here and measure 50 down here. I just want to take this same line from the beginning to the origin. Take this same straight line, just take it somewhere here, and draw the straight line. So that'll be my reference point, right? And I'll just bring down. I'll bring down this on it. So just bring down this on it, so that I can have my horizontal and vertical line. Just bring down this on it. And I'll put my 50 degrees. 50 degrees. So 50 degrees. So it's for me to use my protractor upside down. 50 degrees. So my 50 degrees somewhere here. As you can see, 50 degrees. That means it should be here. 50 degrees. And if I use my ruler, the length of BB knot is 30. According to the question, 30. So I'll look for 30. So from here to here, this 30. That's 30, right? This 30. So now this is my diagram. I've drawn out my diagram. So this is what I wish to. Yes, this is my diagram. So my diagram is out now. For those that cannot draw, this is how to draw the diagram. Now, the question says I should find the angular acceleration of angular acceleration of AB, that's the angular acceleration of this place, and the angular acceleration of this place, BB naught. So the angular acceleration of AB. Now, the reason why I ignored the ACB, is because that's a coupler. It's a coupler, and the angular velocity of the angular velocity of AC is equal to the angular velocity of CB, which is also equal to the angular velocity of AB, because they're couplers, so they will move with each other. So AC and AB something like this. AC and AB something like this, right? This A, this C, and this B, right? So AB, so they are AC and AB are connected to AB, right? So that means however AB moves, that's what AC and AB will move relative to it. So if AB moves like this, AC will move something like this, you get. So they will move the same angular velocity. That is, AC and CB are moving with it. Since they are all coupled together, they will move with the same velocity. So that's why I'll be ignoring this part of the diagram. So from the question, they said OA. The question says that OA equals to 258 rad per seconds. Then AB equals to 2 rad per seconds, and BB naught equals to 4.08 rad per seconds. And also they said the question says OA, the angular acceleration, that is angular acceleration for OA, equals to 10 rad per second square. Meanwhile, all these are angular velocity, and this one is also what? Angular velocity. I know that acceleration has to, if you are drawing acceleration diagram, it has two components. It has the radial, or which can also call the normal, and it also has the tangential, AT. And the formula for AT equals to alpha times the radius of that link. While for A normal, it is omega square r, that is the radius, or you can say V square over r. You can say V square over r. You can say V square over r, yes. You can say V square over r. So how do I get my radial? Now, I have to get the radial of each component. So for me to get the AR of OA now, AR of OA is going to be AR of OA, yes, to be 2.58, then times the radius is what? Square, times what? 0.3, because you know we are changing to meter. I know since this is 30 centimeters, 30 centimeters equals what? 0.3 meter, right? And that will give me 1.997 meter per second square. Right? And now yes, meter per second square. Now I also have to get my ARAB, and that's what. So they said from the question says that ARAB, the omega, that is ARAB was 2 square, then times the radius is 0.5, and that will give me 2. For ARBB naught, that's 4.08 square times 0.3. This is equal to what? 4.99, right? 4.99. And yes, I think I've gotten the A tangential. So okay, yes, I'm going to get my A tangential for A tangential of OA now. It's going to be equal to AR alpha r, which is what? 10 times 0.3, and which is equal to what? 3, right? So now it's just for me to get draw the velocity acceleration diagram and get my acceleration from there. So now before I draw my acceleration diagram, I know that this place, this A O B naught, right? B naught. So I can say that the velocity of B, or don't say velocity, I can say the acceleration of B relative to A is equal to the acceleration of B minus acceleration of A, because B is relative to A, so to be sorry, the acceleration of B relative to A will be acceleration of B minus acceleration of A. I think there are two components for each, so I'm saying that acceleration radial of B relative to A plus acceleration tangential of B relative to A is equals to acceleration radial of B plus acceleration tangential of B minus, oh, there's a mistake before I go to this. There's a mistake. So it's supposed to be, so for me, I'll go here, I'll say A B relative to A. So I'll take this one to the other side, then plus AA equals what? AB, right? So therefore I can say now for each component I'm having A B relative to A radial plus A tangential of B relative to A, then plus A radial of A, then plus A tangential of A equals to what? A B radial plus A B tangential. So just for me to divide each component, A B plus A and A. So I'll get the two components, that's radial and tangential of B relative to A. The two components for the acceleration of this link, this OA. OA is same as A. So OA, because this is fixed, so the acceleration here is just for, you get, it's like me saying A relative to O is going to be equals to what? AA minus what? AO. And since AO equals to 0, so I'm saying AO equals what? AA, right? That I'm just using that A. So now A radial of this place and A tangential of this link, then plus A radial of this link, that is A. So now, so from my question so far, I have this is it here, 1 point. Yes, I have this. I also have tangential here, and this is it here, this 3 is the 3, the value of 3 we got here, 3. Then also, so I have 1 2. I also have this radial, that's for 2, this 2 here, it's for this 2 here, 2. And lastly, I have this one, so I can first draw this 2, draw this 3, then, so let's go to the acceleration diagram. So the first thing is that, for the radial is always on the link. So since this acceleration, so, if you apply a velocity, like if this place moves with an angular velocity here and there's an angular acceleration, so the link, the tangential acceleration will go this way. It will go perpendicular to the link. It will go perpendicular, this is at 90 degrees. Now since it's going this way, the radial will go into the link, but it will be on that link. It will go excuse me, it will go into the link, but it will be on that link. It cannot go out of the link. It's just like we are saying centrifugal force. It cannot go out of the link. It will go. There's a force that is making it, that's pulling it into that link, into that direction of the link. So it's going to go into the link. You get? Now, since we say B relative to A, the tangential will go like this, right? And the radial will go into the link. Same thing for this one now. The radial will go into the link. You get? So we have sort out the direction. So we know the directions for all of them, and we know the magnitude. So it's time for us to draw the acceleration diagram now. So now, for me to draw my tangential, I know that for my radial now, I've said my radial is going into the link, while my tangential is going out of the link. So I can start with my radial. Let me start with my radial. So let me assume that this is my origin here. My origin is here. So that's where my origin is. So I'll first drop my radial. So just want to look for a way to just bring this guy. This is my radial now. I want to bring this. I want to draw this guy close. Yeah. So just want to put this on it. Put this on that part I want to draw out. I want to draw it on this place like this. So just put it on it and place my ruler here and just drag my diagram out. So the length of my radial for OE is 1.9. I can say 2. So let me just, so I'll measure 2. 1.99. 1.99. Okay. So I measure 2. So if I'm measuring 2, that'll be from here to say here. Okay, look at it. So let me say this 2. This 2, right? So, and the other one now. So now the tangential is going to be perpendicular to it. So it's going to be going outside, like what I drew here. It's going to be going outside like this. So it's supposed to be coming. So where I stopped, this is my origin. Where I stopped the radial, continue the tangential. So the tangential is supposed to go this way. So it's supposed to be perpendicular. So I can just, so I don't even need to go far. Just place this one on it and let me show you this one is. So I can use let me use the small line. Let me use the small one. So that's it. You don't even need to. Just going to go this way. Get and measure according to what I have here. The tangential is 3. So I measure a length of 3 on it. 3. 3. So this is my A radial of OA, and this is my A tangential of OA. I have my A tangential of OA. So if I move on, the resultant of both A tangential and A radial for OA is going to be my acceleration. That is radial acceleration for OA, and the tangential acceleration for OA. The resultant of both is my acceleration on OA. That is, if I just draw a dotted line from here, so I'm saying that this place, this acceleration here is OA, and that's my acceleration for OA. So now, where I stop now, I've drawn acceleration for OA. You know, this is OA now, right? Now I've drawn my radial. This is my radial. I've drawn my tangential. Now where I stop, you know, I'm still on the left. This is the left hand side. This is the left hand side, and this is the right hand side. Now what separates them is equals to. So I'm going to draw everything on my left hand side. I'm just going to continue it. So you know what I first did was I drew it. Then where I stopped it, I continue my tangential OA. Now where I stop here now, I'm going to continue my radial because I know my radial, I know the value of my radial, I know the magnitude, and I know the direction. But I don't know the value of this tangential. So let's first draw the radial first. If I draw the tangential. So if I want to draw the radial now, I know the radial is supposed to go this way into the link like this, right? I know it's supposed to go this way, and I know the magnitude. That's how I'm going to draw it next. So I'm going to trace it down from here. I'm going to trace it down from here. See, on that link, just place it there. I'm going to trace it down from here. Just going to trace it down from here. See it? Then just to where this place is. Then I'll draw a thin line. Then I'll measure. What I have on it is 2. So I'll measure 2 on it. 2 from 1 to 2. So this is my A radial of what? B relative to A. Of B relative to A. That's my A radial of B radial. So I've drawn 1, 2, 3. Now it means A, B, A. That's the tangential. That is the tangential acceleration. Now I know the direction of my tangential acceleration. It's supposed to go up. No, it's not supposed to go up. I was just using this as an example because I said it. I've not said it, but let me just say it. So if we were to draw the velocity diagram, you know the velocity is the same. The velocity diagram has the same direction. The velocity has the linear velocity has the same direction with the tangential acceleration. So if my linear velocity is going this way for this first link, or the other link is supposed to go opposite, that is supposed to go downward now. Because this one is going up, it's supposed to go downward. So that means for my angular acceleration too, my tangential acceleration, since it is going up here, the next link, which is this, is supposed to come downward. Assume it was going like this way for this one. I know it's coming down, looking at it. For this one, it's going to go up. But from the question given to us, it's going this way. So that means this one is going to come down. That means now my tangential for this guy is going to come downward. And this is perpendicular. It's perpendicular. So I can either trace it from here. But since I've drawn the radial already, I can just trace it from the radial already. So I just draw it downward. Now I don't know the magnitude, so I just draw a straight line. I'll just stop. So I just still put my A tangential of B, A. Now I'll move to the next line. I'll move to the right hand side. I'll move to the right hand side, which is what? ARB. move to the right hand side, which consists of ARB plus ABT. Now, I know my value for ARB, but I don't know my value for ATB. I don't know the magnitude, but I know the direction here. I know both the magnitude and the direction. Yeah, so I'll first start with this. So the magnitude, looking at it, the direction is going downwards. The direction is going downward, and the magnitude is 4.99, which I can say 5. From what I have here, the magnitude is, so looking at it, is 5. 4.99, which I can which I can approximate to 5. So now, it's going to, so I'm going to start from origin now. You know, I finished with the left hand side, and I started from the origin for the left hand side. So I'm starting for the right hand side. I'm going to start from the origin again. So now, I'm going to start from the origin, the same way I did it. So now the radar is on this link, so I'm going to place this here on that link. I'm placing it on that link, and I'm just drawing into the origin. Yeah, this is the origin. This is the origin. So I'm going to draw, and I'm going to measure 5 on it. 5. So I'm going to measure 5 on it. So it's coming downwards. Now don't forget your arrow. It's very, very important. We went this way like this. And for this one now, O. So I'm going to put, now what I just drew here was acceleration of RBB naught, right? RBB naught. RBB naught. And this 5 meters. This 5 meters. So I didn't say this earlier, but the scale I'm using for this acceleration diagram is 1 centimeter equals 1 meter per second square. So it's exactly what I have here. I'm just drawing as my acceleration diagram. So now, so for the other, I just finished drawing this now. Now I have to draw the tangential. So and I know that the tangential is perpendicular to it, right? So since the left hand side is equal to the right hand side, that means the last man we draw for the left hand side, which is A tangential of B relative to A, must touch A tangential of B, which is on the right hand side. That is, both of them must touch each other. And since we already said A tangential of B relative to A is coming downward, that means A tangential of B on the right hand side must go to the left to touch A tangential of B at a point. So now I have to first draw the tangential of this. So you know it's going like this, so it's going to go this way too. This is A tangential of B naught. A tangential of B naught, or A tangential of B. So that means where they cross at each other, because you know they must touch, since they are equals to each other, they are equivalent to each other. So wherever they cross each other, so yeah. So this is my A tangential of B naught, and this is my A tangential. So for me to I'll just have to cross check what's the length. So now let me check what's my A tangential of. So my A, I'm going to get my A tangential of B naught and A tangential of BA. And my A tangential of B naught, from what I have here, is 7.8. Let me move my camera a bit downwards. So my A tangential of AB, that is B relative to A, is 7.8. And my A tangential of, no, that's, sorry, A tangential of B relative to A, or A tangential of AB, is 7.8. And A tangential of BB naught is also, okay, this is 7.7. So this one is 7.7. So since I said centimeter, so I can put it as meter per second square. I can put this as centimeter per second square. I got 7.7 centimeter, which is same as 7.7 meter per second square. According to me. Now, I said it earlier that the resultant of the radial and tangential will give me the acceleration of that link. So for me to get acceleration of that link, just for me to just trace a dotted line. So this is the acceleration of B naught, that's the resultant, for B relative to A, so I have to, for me to get the resultant, just trace on that, on the where the tangential and the radial stops. Just trace it, same line. This acceleration of B relative to A, or AB. So it's like this. Let me show you. So it's like this. Let's say I have my A radial for a component here, and where I do this like this, and I finish my tangential here, A tangential of B, right? Now the resultant, this is the resultant. So the resultant is going to go this way, right? That's the resultant. So you have to put your arrow too. Don't forget to duplicate your arrow. So the question asked us to find the angular acceleration of link AB and BB0. So we just have to measure the tangential acceleration for link AB and measure the tangential acceleration for BB0, and we'll just use the formula to solve out for angular acceleration. Tangential acceleration, that is AT, tangential acceleration is equal to what? Angular acceleration times the radius. That means my angular acceleration equals to what? The tangential acceleration over the radius. That means angular acceleration for AB is going to be equal to and tangential acceleration of AB over the radius of AB, that is the length of AB, which is equal to what? 7.8 over 0.5. And if you punch your calculator, you get 15.6 rad per second square. Now the angular acceleration for BB0 is the tangential acceleration for BB0 over the length of BB0, right, over, which is equals to 7.7 over 0.3, and that's equals to 25.67 rad per second square. And that's all for this question. So just for you to be able to get your angular acceleration. So the reason why we didn't do the velocity diagram, which we were supposed to first draw before we get, was because from the question we're given the angular velocity, and that's what we needed most to get the angular acceleration.